In this example problem, we're going to determine at least approximately the orbital period for the Apollo 11 command module going around the moon. So it was in an elliptical orbit, and the dimensions of that orbit were about 100 kilometers altitude at the closest to 122 kilometers away from the moon at its furthest. This is from the Encyclopedia Britannica article. So on average, let's say the altitude was about 111 kilometers. I want to do this for circular motion. So it's not a big cheat to do this. We'll get the correct answer. So the altitude average 111 kilometers. We're going to assume the orbit was circular instead of an ellipse. And again, that's legal to do here. We're not going to get a terribly wrong answer. We're going to ignore mass concentrations in the moon that do affect the orbit, but we're not going to include that effect. We're going to do a simple calculation here for the Apollo command module in a circular orbit around the moon at an altitude of 111 kilometers. We want the period using the principles of centripetal force and gravity. So let's make a little drawing here. The circle around the moon is the orbit of the command module. The concept is that the centripetal force is being provided by the force of gravity. The expression for centripetal force is mv squared over r, and the expression for the force of gravity, Newton's expression, capital G is the constant of gravitation, then times the two masses involved, mass of the moon and mass of the Apollo command module. The A here on both sides stands for the Apollo command module. It is important on this centripetal expression that you use the object that's in motion. It would be incorrect to put the mass of the moon in this place. mv squared over r, the m must be the mass of the object that's moving in the circular motion. So we can simplify this, of course, a little bit. M sub a appears on both sides. It's going to cancel. This r is the distance from the center of the moon to the orbit. That's the same on both sides, and one factor of r will cancel on the right side in the denominator. So let's go a little further here. We're trying to come up with the time. Now the time does not appear in this expression as I have it now, but we can bring in the time information using the speed, the velocity, and we just need the magnitude of the velocity, we need the speed. So this first step we've simplified by eliminating mass of the Apollo command module and eliminating one factor of r. Pause the video if you need to inspect this and do some work on your own to convince yourself this is the correct simplification. Then the speed is equal to distance divided by time. So our speed is 2 pi r, the circumference of the circle, divided by the period of the orbit. This capital T stands for the period of the orbit. I need to substitute for v squared, so we're going to substitute for v squared. We get 4 pi squared r squared divided by t squared, and that again is equal to capital G, mass of the moon, divided by r. So we can solve this for t squared and come up with this expression. To get to this point, here I've multiplied both sides by t squared, and I've divided both sides by g, mass of the moon, and I've multiplied both sides by r. So the t squared is computed by 4 pi squared r cubed divided by g and mass of the moon. Now the r. The r is from the center of the moon to the spacecraft. It is not the altitude. R is from the center of the moon to the spacecraft. R is not the altitude. To find r, I have to add the radius of the moon to the altitude. So you can find the diameter of the moon in various tables, 3475 times 10 to the third meters, 3475 kilometers. I have to divide that by 2 to get the radius of the moon. Then we're going to add it to the altitude. And it's important to have meters for both of those. So I come up with an r value, 1.84 times 10 to the 6 meters, roughly. You should pause the video and start to gear up your own calculation, putting numbers into this expression. Then taking the square root of both sides, So 4 pi squared, the r value cubed that we found, the constant of gravitation here, at least an approximate version of that constant, and then approximately the mass of the moon. And that's 10 to the 22nd kilograms, if you can't read that, a little bit small. 10 to the 6th for the meters for the radius of the orbit. 10 to the 22nd kilograms for the mass of the moon. So pause, do that calculation. You should have 7.16 times 10 to the 3rd seconds. To convert that to hours, 1 hour is 3,600 seconds. So divide by 3,600, and I find that roughly it was 2 hours. The Apollo command module, so after it kind of dropped off the lunar lander, is going to be back in 2 hours' time, and then another 2 hours roughly. 1.99 hours for the period of the orbit for the Apollo command module around the moon. So if you enjoy this type of videos, want to learn some more about physics and astronomy, these 2 websites have lists of the videos with a short description, how long the video is, and a link directly to the YouTube video. If you enjoy the YouTube videos, please subscribe to my YouTube channel. That's free, no cost.